Alright, hello class. In this particular lesson we're going to be looking at infinite limits. And this is a closer look at the 1 over 0 case. Well, maybe not 1 over, but a constant over 0 case. All the way back in our first video we were talking about how vertical lines give us a undefined slope in terms of being a constant over 0 whenever we go about that. And I mentioned that if you think about slope being a measurement of steepness and an undefined constant over 0 slope gave us a vertical line, we can almost think of that as an infinite slope or an infinite amount of steepness when it's basically just a vertical line. It turns out that when we are talking about a constant over 0 case, let's say a non-zero constant, what we're talking about is basically infinite limits, blow up, right? So let's take a closer look at some of this stuff, but at the end of the day, what we need to know, okay, is that a constant over 0, a non-zero constant over 0, is going to give us blow up like we have here with this asymptotic behavior. Alright, if you remember this little equation that we were looking at originally, this 5 over 0 equals x, that's equivalent to trying to solve this equation that 0 times x equals 5. Okay, so this is, of course, undefined. There's no solution. Okay. However, we can still use limits to analyze what's going on given certain situations. And what do I mean by depending on the situation? Well, let's think of something like this. Let's let f of x be 5 over x, and let's say g of x is 5 over x squared. Okay, then if we try and look at f of 0, that's going to give us 5 over 0. And g of 0 is also 5 over 0. However, right, so these are both undefined. However, they're going to behave differently around 0. Right? So when we have x equals 0, they're both undefined. We don't really get much useful information. However, remember the limits tell us how something behaves, right? That's what the limit is for. So if we instead look at what's going on with the limit as x goes to 0 of both of these, we'll actually see some behavior that we can describe. Okay, so let's start with some tables, and then we'll look at the graphs, and we'll talk a little bit about what's going on whenever we have this constant over 0 case showing up. Okay, here I've set up a table, and I'm going to start looking at values really close to 0. So I'm going to start with, say, 0.1, then 0.01, then 0.001, 0.0001, and I'll do one more, 0.00001, and I'll do the same over here for the 5 over x squared. Okay, so when we plug in 0.1, just to show you sort of what's going on, 5 over 0.1, well, 0.1 is 1/10. Okay, in fact, we could have done 1/10, 1 over 100, 1 over 1,000, right? 1 over 10,000, etc. Okay, so when we do this, what happens is we're dividing by fractions with larger and larger denominators. So this will be 5 times 10, right? So that's going to give me 50. Whereas here, for the 1 over 100, that's going to give me, so the 5 over 0.01, that's 5 over 1 over 100. So that's going to be, when we invert and multiply, 5 times 100. So that's going to be 500. Then following this pattern, we're going to get 5,000. Then we'll get 50,000, 500,000. And you could probably expect that if we added another 0 here, we'd be adding another 0 here. Okay, so essentially, for x given as any 1 over 10 to some power n, right, 1 over 10 to the n, that x value, or that y value is going to be 5 times 10 to the n. Right, so we're just adding that many zeros on. So this just gets larger and larger, right? 5 over x gets arbitrarily larger. It gets larger as x gets smaller. So this gets larger, right, and larger as x gets smaller and smaller. Okay, so this is definitely a does not exist type of limit. However, it does have a behavior we can describe. So let me write some of that down. Okay, so this is definitely a does not exist behavior, and that's because f isn't getting closer and closer to a single number. Okay, however, it does follow a pattern, right? And that pattern is basically it continues to blow up, get larger and larger as x gets closer and closer to 0. We're going to see the same behavior here because when x is 1 over 10, 5 over x squared is going to be 5 over 1/10 squared. So that's going to be 5 over 1 over 100. So it starts off even higher, right? Because it's going to, when we invert and multiply, be 5 times 100. So it's going to be 500. Then when x is 1 over 100, 100 squared is 10,000. Okay, so that's going to give us 50,000. Okay, then 1 over 1,000 squared. Well, 1,000 squared is, we're going to get 6 zeros. Okay, so that's going to be 5 and then 6 zeros. So what is that? That's 5 million. Okay, and in general, 10 to any power, if we square it, is just going to have double that many zeros. So if it had n zeros, now it will have double that. So if it started with 2 zeros, or sorry, if it started with 1 0, now it has 2. If it started with 2 zeros, now it has 4. If it started with 3, now it has 6, etc. So basically 1 over 10 to the n. If we give it that, the 5 over that value is going to be 5 times 10 to the 2n. So it is getting larger way faster than 5 over x does. But if you think about what x squared does, x squared increases a lot faster than x does. So when this thing is increasing, it is going to be increasing faster than the one based on x does. Okay, so here's what we say. Okay, when behavior like this happens, yes, it is a does not exist, but we don't tend to put does not exist unless we're talking about a two-sided limit where it doesn't match. What we say instead is this. Okay, so here's what we'll say, that the limit as x goes to 0 from the right, because that's all we've checked so far, of 5 over x is infinity. Or we'll say that the limit as x goes to 0 from the right of 5 over x squared is infinity. Now, keep in mind, infinity is not a number. Infinity is a concept. Infinity basically means we increase without bound, right? Or you can think of it as we increase without limitations, okay? We blow up. You may have learned about this in the past as a vertical asymptote, right? When the limit as x, say, goes to 0 from the right of f of x, if that's infinity, this corresponds to, we have a vertical asymptote, okay, at x equals 0. Okay, we'll talk a little bit more about this in just a second. I know you all have probably learned about asymptotes in your pre-calc class, but now we will have a better way to talk about them now that we have limits. What I want to do real quick, though, is I want to look at this from the negative side, because all we looked at so far was the positive side. So we'll do, say, negative 0.1, negative 0.01, negative 0.001, negative 0.0001, etc. Okay, now this shouldn't affect things that much because if we go back up to this work here, if I divide 5 by the 0.1, that's going to be dividing it by negative 1 over 10, right? This is now just negative 1 over 10, which will give us the same value except negate it, right? So all we're doing in f, okay, is negating our values, right? So this will be negative 50, this will be negative 500, this will be negative 5,000, and this will be negative 50,000, etc. So when we plug in a negative 1 over 10 to the n, we should just get negative 5 times 10 to the n. Okay, so this, on this side, we are getting still larger and larger, but in the negative direction. Okay, and I'm going to be using the term larger and larger here because what I'm talking about is the numbers themselves get larger and larger. It's just in the negative direction. I don't want to use the word smaller, right? When I talk about large and small, I'm talking about the magnitude, just the number itself, while positive or negative is about the direction. That's going to be really important as we go further. Okay, so this is what happening here. It's basically the same behavior except we are blowing up in the negative direction. However, over here for the 5 over x squared, nothing should change. Because if we put a negative, if we look back at our work over here, if we put a negative in this 1 over 10, squaring it keeps it positive. Right? And if we make this negative 100 squared, that's still 10,000. And I didn't put a square here, I should have. But if we put a negative in here, that doesn't change that. And if we put a negative in here, the square gets rid of the negative. So we will have the same values. We'll have 5,000, we'll have 50,000, we'll have 5 million, okay, etc. So this still gets larger and larger, okay, as x gets smaller and smaller in the negative direction. Okay, so here's what we say in this particular case. Okay, so based on what we got in the table, the limit as x goes to 0 from the negative side of 5 over x is negative infinity. Negative infinity is how we say that we get in or decrease without bound. Okay, this is blow up in the negative direction we just talked about. And then, however, the limit as x goes to 0 from the negative side of 5 over x squared is still positive infinity. So I will often write positive here in front of my infinities just to really be specific. Most people don't do that, but I do like to do that just to be absolutely certain that I'm not which direction I'm talking about. Okay, and then from here we can actually talk about the two-sided limits, because for the limit as x goes to 0 from the right and the left of 5 over x squared are both infinity, so we can say, okay, so the limit as x goes to 0 of 5 over x squared, we just say, whoops, I don't know what happened there. I did put a plus. We can say it's plus infinity, that the limit as x goes to 0 on both sides of 5 over x squared is infinity, where in this case the limit as x goes to 0 from both sides of 5 over x, well, it's positive infinity on one side, negative infinity on the other. This is what we say is does not exist. Okay, since it's positive infinity from the right and negative infinity from the left, whereas here both sides match. Okay, but do keep in mind, an infinity is still a form of does not exist. However, we use it to describe the behavior. Right? The behavior is it blows up. Okay, so here I've just written that down. Basically that when the limit is a plus or minus infinity, it's still a form that does not exist. However, we just use that to describe its behavior. All right, so just to show you what's going on with a graph, here is 5 over x. Okay, and we see the blow up that we were talking about. As x gets closer and closer to 0, the y values blow up. Okay, now if I zoom in real close here, you see on the x-axis I'm looking at tick distances of 0.05 to 0.1, 0.15, etc. And on the y's I'm like 20, 40, 60, 80, etc. And as I move my x's closer and closer and closer to 0, you start to see, hopefully there, that as that happens, the y values just keep blowing up. Okay, and I can move this down. Now the y's are on a tick mark of 50, and as we move closer and closer and closer, we just keep getting off the screen. So, whoops, I don't need to move that side. So now we're all the way up here over 500, and we keep, no matter how far we zoom out, we can always get close enough to zoom right off the graph. Okay, so essentially, and you can see here how when I go back to the default view, we're real close to 0, but we have to zoom way, way, way far to even get close, right, to where our point is. Okay, so that's what we mean when we're talking about blow up. Now this was 5 over x. Okay, let's move that. And then now here is 5 over x squared. And we can see on both sides it's blowing up in a positive direction. Right? And we can zoom out as far as we want and see that on both sides here, the red graph is shooting up to positive infinity, whereas with the blue graph, it goes up to positive infinity on one side and negative infinity on the other. Okay, this is, like I said, this using the infinities is basically just describing the behavior. What type of blow-up do we have? All right, now let's take a look at just a graph here and say that we want to find the limit of this function. Let's call f of x as, let's start with x goes to 1. So when x is going to 1 from either side, we see that the y values here are blowing up on both sides. Okay, so what we could say is, if we jump back here, is that the limit as x goes to 1 of f of x is infinity. Right? Because as we approach 1 from either side, we get, well, blow up. All right, now to show here a little, maybe a little more graphically, as x gets closer and closer to 1 here, we see that the y values get larger and larger and larger, and we blow up right off the screen. Okay, so from the right, this graph is blowing up to infinity, and we'll see the same thing from the left. Okay, so as we approach from the left, we're getting closer and closer to 1, but the y values are getting larger and larger. And you can even see when I get right to 0, it tells me infinity. So when we're at 0.99, we're at almost 2,500. And when we take one more step, the graphing software just straight up tells me infinity. Okay, so we get that behavior on both sides of 1 here. Now, if I want to look at the limit at -1, so from the right, as we get closer, now instead, as we get closer to -1 from the right, our y's are jumping down to negative infinity. And you see, once we get there, my software even says negative infinity. Okay, but we see here it's down to almost negative 2,500 when we're at negative 0.99. All right, and if I take a step closer, like negative 0.998, we're all the way at what looks to be about 62,500-ish. Okay, and so from this side, we're definitely dropping down to negative infinity. You can see the point there shooting down. And then if we do the same thing from the left side, okay, now from the left, as our x's get closer and closer to -1, our y's are blowing up downwards. Okay, so we could say that for this particular graph, that the limit as x goes to -1, and this is from both sides, is negative infinity because it has negative blow up. Okay, so this is telling us that we have something like this at x equals 1, and this one's telling us we have something like this at x equals -1. Okay, now that we have limits, we have a much better way to describe what vertical asymptotes are, because that's what these guys that we just found are. These are vertical asymptotes. All right, so I'm not quite sure how your pre-calc class may have defined vertical asymptotes. Usually it's in a very hand-wavy kind of way, or a not very robust way, but now that we have limits, we can actually just say that if the limit as x goes to a of f of x is plus or minus infinity, or the limit from either side. We don't need it to be blowing up on both sides. So for example, if you had a graph that looks something like this, where it blew up on this side, but say from here on it was fine, this is still a vertical asymptote because we have blow up on just one side. So that's what these guys are saying. So basically, if the limit from either side or both sides, if it's plus or minus infinity, then the line x equals a is called a vertical asymptote of f of x. Now this is important here. It's the line itself is called the vertical asymptote. You need to be careful because your online homework, things like that, the book, it's looking for this usually. Okay, when it asks for what the vertical asymptote is, okay, it's looking for an x equals a. So in this case, for these two, the vertical asymptotes, and I tend to put just the VAs, are x equals 1 and x equals -1. It's not just the numbers, it's the lines, because what it's telling you is the lines that these functions are getting closer and closer to. That's a little more important when we start talking about slant asymptotes. Okay, but essentially the vertical asymptotes, it's telling you what line the graph is getting closer and closer to as x goes to 1 or goes to a. Okay, so if we go back to this graph and I actually graph the line x equals 1, so here's the line x equals 1, and if I move up, okay, and maybe zoom out, you see eventually the graph is getting closer and closer to this line, okay, but never actually touches it, okay, never actually crosses it, but is always getting closer and closer and closer. That is asymptotic behavior. That is what it means to be an asymptote. And so what it means is that the function is approaching this line. That is why, graphing, or not graphing software, but your book and MyLabs and all that kind of stuff is very picky about this. Okay, and here's the line x equals -1, and we have the same idea. The graph is approaching this line. Okay, so when you have a vertical asymptote, it basically means that your f of x eventually approaches this vertical line. Okay. However, this is a function, so it doesn't actually become a vertical line. It just gets closer and closer and closer to that vertical line. Okay. I know that's a very subtle distinction there, but it can be an important one. All right, let's do another example here. If we look at the limit as x goes to 1, on both sides it is blowing up in the vertical direction. Okay, so setting up my little line segment and whatnot again. As we come at 1 from the right, well, the y values shoot right off the graph, and we can follow it up, and we see that it goes basically to infinity, right? It continues to blow up. Here we are, and as we get closer and closer and closer, well, we go right off the graph. And yeah, here we are at 1.019. We're at 1371. So, and as I've zoomed out, you can basically see the blow up here. Now you'll notice here, the way that this is graphed, it
if this is what your calculator gave you, say if you were using a graphing calculator, you'll see this behavior a lot, where it doesn't really show. Maybe if we didn't have these numbers here, it looks odd this way. And I've seen asymptotes not show up on graphing software a lot. So that is part of why we're going to move towards how we can do this analytically without needing the graphs. Okay, so if we zoom back to our sort of more standard position here, we, of course, see that we're blowing up on this side. Now I want to look at the left. Now on the left side, as we approach 1, again, we're blowing up in the positive direction. Okay, we're going right off the screen. Okay, so for this particular function, we could say that for this graph, let's call this graph G. Okay. The two-sided limit as x goes to 1 for G is positive infinity. We have a situation like this. Actually, right, it's a blow up from both sides. All right, now if I look instead now at 3, it should be pretty clear that this is definitely a does not exist limit, because from the right it's going up to positive infinity, but from the left it's shooting down to negative infinity. All right, so to see it with the visualizer here, as x gets closer and closer to 3, the y's just jump right off the graph. Okay, so, and in the positive direction. And when we come at from the left here, in the negative direction, it is jumping down to negative infinity. Okay, so from the right, positive, from the left, negative, the two-sided limit is going to be does not exist. Okay, so we will want to write both sides here, that the limit as x goes to 3 from the right of g of x is positive infinity. However, the limit as x goes to 3 from the left of g of x is negative infinity, and that means that the two-sided limit of g of x does not exist. Okay, however, it's good to have both of these because this tells you what's happening on either side. So now I know that on, say, the right side, the function blows up, but on the left side, it blows up, but in the opposite direction. Right? So this is a very efficient way to talk about how a function behaves at an asymptote. All right, so the vertical asymptotes are x equals 1 and x equals 3. All right, now graphs typically aren't good enough for us. Yeah, graphing software has come a long way, but I don't know if you've seen this sort of behavior before when you graph a function and it does this. It just looks like a jump. It looks like, oh, we come here, then we jump, and what have you. This can happen a lot, especially with our graphing calculators. It can't maybe get close enough. It doesn't realize that there's an asymptote there. There actually is. This function should look like this. But in a lot of graphing software situations, what we'll end up with is something more like this. And it might lead us to think that, okay, the limit is undefined, but it might lead us to think that from the right, it's like 2.2, and from the left, it's like negative 2.2, right? It makes it seem like there's a jump there, but a finite jump, okay? So the question becomes, well, how do we analyze these types of limits without a graph or a table, because clearly a graph or a table have their limitations. Okay, and it turns out that there's a pretty quick way to go about it. Okay, so the question becomes, well, how do we analyze these limits algebraically, i.e. without a graph or a table? So when looking at the limit as x goes to a of f of x, and when we plug in the a, right, if we plug into the a to the f and we get a constant over 0, and that's where c, that constant needs to be non-zero, because if it's 0, then we just have a 0 over 0 case, right? Then we have plus or minus infinity, or always. So then it's just a question of which one is it, okay? So the c over 0 is always a plus or minus infinity, okay? But which one is it, the plus or the minus? All right, and this is always going to happen because if you think about c over something like 1 over 10,000, that's always going to be some constant times 10,000, right? And as the x's get smaller and smaller and smaller, the c over that gets larger and larger and larger and larger. So the c over 0 case is always a plus or minus infinity. It's just, which one is it? Which sides are the different blow-ups on? Okay, etc. So how we go about determining which one it is actually just a little bit of logic for the most part. Okay, so let's take a look at some examples to show how we do this algebraically. All right, let's start with that example we essentially started this whole lesson with, this 5 over x. All right, and I know that if we're looking for, or when considering the limit as x goes to 0 of 5 over x, this is a 5 over 0 case. So I know for a fact it's going to be a plus or minus infinity. All right, so with these types of limits, what we want to do is check on either side. So I'm going to do the limit as x goes to 0 from the right of 5 over x, and the limit as x goes to 0 from the left of 5 over x. Now, in both of these cases, when we plug in the 0, we get 5 over 0 and 5 over 0, okay, which we know is just going to be a plus or minus infinity. Okay, so how do we determine which one it's going to be? Well, from the table, we knew that on the positive side, when we were plugging in positive x's, we were getting positive values, where on the negative side, when we were plugging in negative x's, we were getting negative values. So here's how I go about doing this, okay? I'm looking at values of 0 from the right. So 0 plus, these are values like 0.01, 0.001, 0.0001. These are basically values that are greater than 0. Okay, so what I do is I just put, this is 5 over 0 plus. Okay, and then I make a note to myself that, okay, this 5, of course, is positive. Okay, now this value down here is a positive 0. So you might wonder what in the world I'm talking about a positive 0. Well, every value I plug in here is going to be positive. So I have a positive over a positive. That's a positive. Okay, so this is going to positive infinity. On the other hand, on this side, when we're talking about 0 from the left, well, that's things on the other side of it. So negative 0.01. negative 0.001, negative 0.0001, etc. Okay, so these are all x values less than 0. So I just write in 0 minus. Okay, so now we have, well, the top is positive. The top is always going to remain the same in these cases. The top is positive, but now the bottom is negative. You can think of this as a negative 0, right? Because everything we're plugging in is really close to 0, but on the negative side. So a positive over a negative is a negative. Okay, so really all we're doing is determining whether the fraction we're looking at is a positive over a positive or a negative over a negative or what have you. All right, so it's basically, this boils down to determining if our fraction is a plus over plus, plus over minus, minus over plus, or minus over minus. These two will give me positives. These two in the middle here will give us negatives. So this would yield a positive infinity, and these two would yield negative infinity, negative infinity. And that's really all there is to it. We just need to determine which one it's going to be. Okay, once we do that on either side, then that tells us finally that the limit from both sides of this function, 5 over x, does not exist, right? Because it's positive infinity on one side and negative infinity on the other. However, that's not always the case, since we saw before that 5 over x squared gave us positive infinity on both sides. Okay, so to look at another example, let's let f of x equal 2 minus 5x over x minus 3, and we want to analyze the limit as x goes to 3 of f of x. So f of 3, if we just look at f of 3, that's going to be 2 minus 5 times 3 all over 3 minus 3. So this ends up being, it's going to be a constant over 0 case. So this is 2 minus 15 over 0. So that is going to be negative 13 over 0. This is a plus or minus infinity case, right? A constant over 0. Okay, so now we're going to look at both sides. All right, so I want to look at the limit as x goes to 3 from the right of this and the left. All right, now here's how I like to do this. I already sort of explained that, but I like to plug, when I'm dealing with a plus or minus infinity case or constant over 0 case, I like to plug in the 3 plus. Okay, so this will be 2 minus 5 times 3 plus all over 3 plus minus 3. And the reason I like to do that is because up here it's not going to matter much, because this will be 2 minus 15 plus, and either way the top is always going to be that negative 13. So it doesn't really affect that. However, this is 3 plus. So these are things a little bit bigger than 3. So we're thinking things like 3.0001 minus 3. Okay, which ends up being something like 0.0001. So this is a 0 plus. This is a positive value down here. That's really what we're trying to figure out, is that this is positive, because we have something a little greater than 3 minus 3. So we should have something positive. So that's really what matters here, is that this is positive. Okay, so I have a negative, right, over a positive. Oops. So a negative over a positive Negative over positive is negative. So this side we have negative infinity. Okay, so that's what we have from the right side, from the positive side. Okay, and then I'm going to shift this down to give myself a little more room, and then we'll do from the left. Okay, so once again, we have the limit as x goes to 3 from the left of 2 minus 5x all over x minus 3. So again, I like to put in the 3 minus. So we'll have 3 minus on the top, and then 3 minus minus 3 on the bottom. So again, the top always is going to be that negative 13. That part never really changes. It's the bottom here that we need to look at, because now these are values less than 3. Right? This is something like not 3.001 like it was up here. Now this is something like 2.999 minus 3. So this is something like 0.0001 negative. Okay, so specifically, that's what we are concerned with. This is going to be negative, because this is something very close to 3, but still less than 3. So something smaller than 3 minus 3, this will be negative. So this is a 0 negative here. So this is a negative over a negative, which will come out to be positive. So this is a positive infinity on this side. Okay, so that means at this value here, at 3, we have a situation like this. From the right, it goes to negative infinity. And the left, it goes to positive infinity. Okay, so this is what it will look like at around 3. So that means the limit from both sides does not exist.
All right, let's look at another example here. Let's say our function is g of x equals x squared plus x minus 2 all over x cubed plus 6x squared plus 12x plus 8. All right, this one's going to be a little complicated. And we want to find the limit as x goes to negative 2 of g of x. So if we just plug in negative 2, okay, so we're going to get 4 minus 2 on the top, and we'll get minus 8 plus 24 minus 24 plus 8. Oh, this is a 0 over 0 case. Oh, well, that's okay. We know how to deal with 0 over 0 cases, so let's start working on that over here. We can start trying to do some algebra to work this out. All right, so remember, a 0 over 0 case with limits means more work. Okay, so we're looking at the limit as x goes to negative 2 of this monstrosity, and we're going to try and factor these things. It looks like they'll factor, because here on the top, I want two things that multiply to give me negative 2, but sum up to give me positive 1. So it looks like it will be x plus 2 times x minus 1. And I'll give you a hint here. Whenever you're trying to factor things in a limit that gives you 0 over 0, if the limit's going to negative 2, and it gives you 0 over 0, x plus 2 or something like that is going to be one of the factors. It should be, because when you plug negative 2 in, it's going to give you 0. Now this bottom one's a little trickier. So what we're going to do is, since I have 4 terms, we're going to factor by grouping, right? Since we have 4 terms and they don't all share something, right? Only these 3 share an x, and only these 3 share, say, 2. So we will group them and factor them that way. So in the first group, we can take out an x squared, right? So we'll have x squared, and then what's left is an x plus 6. All right, and then for the next group, we could take a 4 out, and then we're left with a 3x plus 2. Okay, well that does not work out the way I was hoping it to. So what we're going to have to do in a case like this is, if grouping doesn't work, the other option we have is, since I have an x cubed, this might be a cubic form. So for example, if you have a plus b all cubed, this comes out to be a cubed plus 3a squared b plus 3ab squared plus b cubed. And I think we have that here, because if a is x, okay, and b is 2, okay, we would have x cubed plus 3 times x squared times 2 plus 3 times x times 2 squared plus 2 cubed. So when we simplify this, this becomes x cubed plus 6x squared plus, that's 4 times 3, which will be 12x plus 8. There we go. This is a cubic form. Okay, so notice what I just did there when I was doing this problem. I started by thinking, oh, we could factor this by grouping. Let's try that. But that didn't work, so then I thought, since we have an x cubed and this is 2 cubed, and that's what led me to think this, that this is x cubed and this is 2 cubed, it made me think it might be something like this, an x plus 2 all cubed. Turns out it is. Let me show you another thing you can do if you're not sure how to factor this. Okay, this is a bit of a divergence here, so skip this if you want. But what I'll say is that we know we should be able to take an x plus 2 out of this because it's the minus 2 that's causing the problems. Right, and if we're not sure how to factor it, what you can always do is long division. Or if you remember synthetic division, you can do it that way. Synthetic division is great if you have to do it a lot, but if you only have to do it maybe once every, say, 30 problems, you can go ahead and just do long division. And it works with functions just like it does with numbers. I need something that's going to turn x into x cubed, and that's going to be x squared. Right? So we multiply x squared across to get x cubed plus 2x squared, and then we subtract this. All right, so we're going to subtract these two things so that this becomes 0, and then we get 6x squared minus 2x squared, which will be 4x squared. And we're going to bring this guy down. So now I need something that will turn x into x squared. Of course, that will be, well, specifically 4x squared, that will be 4x. So we multiply that through. We'll get 4x squared plus 8x. And then we're going to subtract again. So we'll just change these signs. Okay, so that this goes to 0. And then I have 12x minus 8x, which should give me 4x. Okay, now what I multiply x by to get 4x is just 4, and this should be the last one. All right, let's go ahead and bring the 8 down as well. Forgot to do that. Okay, and so now the 4 times x plus 2, that should give us 4x plus 8. And when we subtract, this will be 0, and this will be 0. Okay, so we get x squared plus 4x plus 4. So this tells us that we can factor, let me write it here, x cubed plus 6x squared plus 12x plus 8 can factor into, we took out an x plus 2, and this is what's left over, the x squared plus 4x plus 4. And that's part of why I gave you that hint. If you get a 0 over 0, you know, okay, that you know you should be able to take an x plus 2 out. And then this can factor without much trouble, because now we're looking for two things that multiply to give us 4 and add to 4. That's going to be x plus 2 and x plus 2. Or x plus 2 cubed. All right, that was a long walk to get there, but if you're unsure on how to factor something, but you know something that can be taken out of it, you can always do that. Okay, so now this x plus 2 will cancel with this x plus 2 and leave us with an x minus 1 over x plus 2 squared. Now, when we plug in the negative 2, now we're at, this will be negative 3 over 0. Okay, so now we know we have a plus or minus infinity. So which one is it? Well, the top, if we put in the negative 2, and in the bottom, if we put in the negative 2, well, here, the top is always going to be negative 3, but the bottom, since we're squaring it, whether we put in plus or minus, right, whether this is 0 plus or minus, we're squaring it. So this will always be positive. Okay, so that means we have a negative over a positive, right? Negative over a positive. So whenever you're left with something squared or to the fourth, that makes this always positive. However, since we have a negative on the top, this is going to negative infinity. And notice I didn't check both sides. I could. We don't really have to here, because whether we put in the plus or the minus, we're squaring it. Something squared, this thing is always positive, essentially. Okay, so this limit here, with all that work, it's negative infinity. Okay, so yeah, this was a pretty nasty example. However, if you can follow this one and do this one, really you should not have any trouble whatsoever with any of the other ones in the homework. So what I wanted to show is that a 0 over 0 case can mean an plus or minus infinity. Remember, the 0 over 0 case just means that there's more work to do. And when you get to that more work, you may find that you actually have an infinity popping up. Okay, so that should be enough for this particular video. That should get you rolling on the homework, and I'll catch you all in the next one. Cheers.